This is part 2 of the 4.08 review. Problem set 79, writing thermochemical equations. Objective, use thermochemical equations to describe heat flow during chemical reaction. Thermochemical equations provide the necessary information for determining the amount and direction of heat flow during a chemical reaction. A thermochemical equation is a chemical equation that shows the enthalpy change, or delta H, for a reaction. The change in enthalpy is written after the written chemical equation. The sign of delta H tells you if the reaction is endothermic, take energy in, or exothermic, releases energy. You can use thermochemical equations to predict the amount of heat that will be lost or absorbed during chemical reaction. So let's look at the remember column. Remember, writing thermochemical equations. A thermochemical equation is based on the reaction of a given number of moles of substance. The delta H for a reaction is specific to the number of moles of a reactant shown in the thermochemical equation. For example, if you double the number of moles that react, you also double the delta H. So that was where we had written before in our notes that if we have 3 times as many of the reactants, we have to multiply the reactants and the product and the delta H value all by 3. The physical states of substances are important in thermochemical equations. Changing the state of either reactants or products will change the value and possibly even the sign of delta H for the reaction. If a reaction is reversed, the sign of delta H for the reaction is also reversed, but the numeral value stays the same. Example 1, calculate delta H for a net reaction. The reaction between hydrogen gas and oxygen gas can be written in the following way. 2 molecules of hydrogen gas plus 1 molecule of oxygen gas yields 2 molecules of liquid water. The delta H of the reaction is negative 571.6 kilojoules. This reaction actually occurs in 2 steps, as shown by the chemical equation. Equation 1, 2 molecules of H2 gas plus 1 molecule of oxygen gas yields 2 molecules of water, which is a gas. And then in the second part, we change gaseous or vapor water into liquid water. What is the enthalpy of reaction for condensation of water vapor in this reaction? Well, we know the first part. We know the end part. So now what we have to do is we basically add the equations together. So when added together, the 2 component equations yield the net reaction shown below. So I put the first equation on top, the second equation below, and I add them together. So I add it going down. I add it here, and you can see I have 2 water molecules that are gas on the left side of my equation and 2 water molecules of gas on the right side, so they're the same, so they cancel. And then you bring down the O2 and the 2H2O liquid. The total enthalpy change for the sum of 2 or more chemical reactions is equal to the sum of the enthalpy changes for the component reactions. Therefore, delta H1 plus delta H2 equals delta H of the reaction, where delta H of the reaction is the enthalpy of the overall reaction, and H2, if we do our algebra, equals the delta H of reaction minus the delta H of the first part. So we just substitute in our values. So here's how much the reaction is. Here's how much the first part is. Use your algebra, solve how much is the second part. And the second part is negative 88.0 kilojoules. Again, if you have problems, please come to office hours. Tip: remember that the delta H value for a reaction is always the delta H for the reaction as written. Any changes to the chemical reaction will affect the value of delta H. Predict delta H for a reaction. Consider the reaction shown below. 2 solid sodium atoms plus 2 liquid water molecules yields 2 sodium hydroxide molecules, aqueous, plus 1 hydrogen gas molecule. Calculate the delta H for the reaction between 4 moles of NaOH and 2 moles of H2. Will heat be absorbed or released during the reaction? Solution. Recall relevant information. Reversing the direction of a reaction requires reversal of the sign of the delta H, and changing the amount of reactants requires a modification of the given value of delta H. Apply. The reaction between NaOH and H2 is the reverse of the equation above, as shown below. So it's the exact same equation, but we reversed it. So what do we have to do to our delta H? Instead of it being negative, it needs to be positive. The delta H value above is for a reaction that consumes 2 moles of NaOH. You must double the delta H value for a reaction consuming 4 moles. So now I want to have twice as much NaOH. So I can't just multiply the NaOH by 2 to get a total of 4. I need to multiply it all by 2. So solve. Go ahead and hit pause if you know how to do it. Doubling the delta H value of the reaction in step 2 yields 367.5 kilojoules times 2, or in other words, 735 kilojoules. So the delta H value for the reaction of 4 moles of NaOH, or twice as much, with 2 moles of H2 is twice as much as well, 735 kilojoules. This is a positive delta H value, so heat will be absorbed during the reaction. Absorbing heat, is that endo or exothermic? It is endothermic. All right, so they have you do the 2 problems at the bottom, and I put it in a Word document to go over. First one says, the reaction of 1 mole of iron metal with 3 moles of aqueous HCl produces 1.5 moles of hydrogen gas, 1 mole of aqueous FeCl3, and 87.9 kilojoules of heat. Write a thermochemical reaction equation for this reaction. Okay, basically what I like to do for these is just kind of break it down into bits and pieces. So I'm writing a chemical equation. Okay, so read it again. The reaction of 1 mole of iron metal with 3 moles of aqueous HCl produces. Okay, so produces, that's my product. So that tells me that produces is my arrow, right? It's my yield sign. All right, so we're going to put that there. And what produced something? Well, 1 mole of iron metal. Okay, so that's my Fe. So Fe plus what? Plus HCl produces, and then I want, it produces what? 1.5 moles of H2 gas. All right, so it produces H2, and what else does it produce? It also produces 1 mole of aqueous FeCl3. All right, so I have that there. Am I done? No. Let's go back and see what else we have. We have 1 mole of iron metal, okay, and 3 moles of aqueous HCl. Okay, 3 moles. How are we going to represent the fact that there's 3 times as much HCl as there is compared to the metal iron? We're going to put a 3 right there. You could put a 1 in front of the Fe. You don't have to. So produces 1.5 moles of H2 gas. All right, so what number do we put in front of the H2? We put 1.5. And 1 mole of aqueous FeCl3. All right, so we would put a 1 there. The book says this part is right. Honestly, you don't want to have decimals, so you would probably multiply everything, but for this, for now, we can leave it. Okay, am I done? No, because what else did it produce? It not only produced hydrogen gas and aqueous iron chloride, it also produced what? Heat, right? Okay, so we got to put that over there. It produced delta H equals 879 kilojoules. Oops, 87.9 kilojoules. Okay, so it produced heat. Does that mean heat is being taken in or heat is being given off? If it produces heat. Well, it produces heat, so the heat's going out. So is it endo or exothermic? It's exothermic. So is it positive or negative? It's negative. Okay? Are we done? A good way to check if you are done is to go through and simply just start making lines through everything that we used. Okay, we didn't talk about that, but 3 moles, that. Okay, if you do what I'm doing right now, you'll notice that there's some words that I'm not crossing off that we haven't taken into account yet. Okay, oh, look at that. Metal, aqueous, gas, aqueous. Oh yeah, we have to write the phases. So, what phase is the iron? Well, if it's metal, it is a solid. All right, what about the HCl? What phase is that one? It's aqueous. What about the hydrogen gas? Well, as I just said, it is a gas. And my iron chloride is aqueous, which is AQ. All right, so we have down phases, we have down the moles, and we can check it out. Yep, we got our delta H is negative. They did it as 3/2 instead of 1.5. Now, what if it told you that you need to have all of your coefficients be whole numbers? What would I have to multiply the 1.5 by to make it a whole number? I'd multiply it by 2. But remember, I have to multiply everything by 2. Okay? So I have to multiply everything by 2 in order to get rid of that decimal. And if I do, let's see, 1 times 2 is 2, 3 times 2 is 6, 1.5 times 2 is 3, 1 times 2 is 2. Am I done? No. We got to multiply the 87.9 times 2 as well. So it'd be negative 175.8. Negative 175.8. So this answer is more correct, but this answer is all that the book expected you to be able to do. All right, let's go ahead and look at problem number 2. A chemist must add 3,352 kilojoules of heat to 2 moles solid Al2O3 to cause it to break down to form 4 moles solid Al and 3 moles gaseous O2. Write the thermochemical equation. All right, so hit pause and do this on your own, and then I'll start going through it. All right, so I'm adding 3,352 kilojoules to 2 moles of solid Al2O3, and it breaks down, okay, so that's where my arrow is going. It breaks down, that's my yield, into aluminum. Oh, how much aluminum? 4 moles of aluminum plus 3 moles of gaseous oxygen. So gaseous, go back to my aluminum. It said it was solid. All right, and then at the end, I write what? My delta H equals 3,352 kilojoules. Is it positive or negative? Well, the chemist must add. So that means, are you putting energy in or taking it out? You're putting it in. So is that endo or exothermic? It's endothermic. So is it positive or negative? It's positive. All right. And check our answer. And there it is. So again, the reaction, as it says here, there we go. The reaction absorbs heat. So delta H must be positive. And there we go. Okay, as always, if you have questions, let me know. Otherwise, go ahead and take the quiz if you're ready.